Sometimes the world around us holds secrets so profound, so utterly bizarre, that they make even our wildest dreams feel mundane. Think about those old tales of sea monsters, the whispered legends of creatures lurking in the crushing darkness of the ocean's depths. Or perhaps you've stumbled upon strange facts about ecosystems thriving without sunlight, fueled by volcanic vents. These aren't just stories, they're glimpses into a reality far stranger and more magnificent than we often imagine. You see pictures of the colossal squid, its eye the size of a basketball. Or perhaps you've heard whispers of the giant isopod, an armored tank scuttling across the abyssal plains. These aren't just anomalies, they're the norm in a world so far removed from our own. A world that makes even our most fantastic sci-fi concepts seem small. What if I told you that in this very world, right now, there are insects? Not true insects, of course, but their distant evolutionary cousins that dwarf anything you've ever seen on land. We're talking about creatures that defy our terrestrial understanding of size, growing to proportions that would make a house cat look like a toy. Imagine a spider the size of a dinner plate, or a woodlouse as long as your forearm. These aren't exaggerations. These are the realities of the deep sea. You probably won't survive a visit to their realm without some serious multi-million-dollar equipment. And even then, it's a terrifying, alien environment. But don't worry, you don't have to go there to experience it. You and I are going to journey into that lightless, crushing expanse, exploring the titans that call it home, and unraveling the mysteries of abyssal gigantism. Before you and I get into more detail, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. When you think about the deep sea, you probably picture barren plains, cold water, and endless darkness. And you'd be mostly right. But within this seemingly desolate environment, life has not just adapted, it has exploded in unexpected ways, particularly in terms of size. This phenomenon, where deep-sea creatures grow significantly larger than their shallow water relatives, is known as deep-sea gigantism or abyssal gigantism. It's one of the most intriguing and perplexing biological mysteries of our planet. Why do these creatures, living in such extreme conditions, become so enormous? It's a question that has puzzled marine biologists for decades. And while we have some compelling theories, the complete answer remains elusive, a whispered secret carried by the deep currents. One leading theory centers on food scarcity. Imagine a desert, but instead of sand, it's water. And instead of sparse plants, it's just emptiness. Food in the deep sea is incredibly rare, primarily consisting of marine snow, tiny organic particles drifting down from the surface, or the occasional large carcass, like a fallen whale. In such an environment, being larger can be an advantage. A bigger body allows for a more efficient metabolism, meaning you can conserve energy better during long periods between meals. It also allows for larger food storage capacities. Think of it like a camel in the desert. It stores fat to survive long journeys. These deep-sea giants store energy in their larger bodies, allowing them to endure prolonged periods of starvation until the next meal drifts by, or they stumble upon a lucky find. This isn't just a hypothesis. Observations of many deep-sea species show incredibly slow metabolic rates compared to their shallow water counterparts, a direct consequence of this energy-saving strategy. But food scarcity isn't the only piece of the puzzle. Another significant factor is the cold temperature of the deep ocean. At depths below about 1,000 meters, the water temperature hovers consistently around 2 to 4 degrees Celsius, 35 to 39 degrees Fahrenheit. This frigid environment significantly slows down the metabolic processes of cold-blooded creatures. When metabolism slows, organisms tend to grow more slowly, but crucially, they also tend to live longer. With a longer lifespan, there's more time to grow, even if the growth rate itself is slow. This live slow, grow big strategy seems to be a common theme in the deep. It's a trade-off. You might not be the fastest, but you'll have more time to reach a truly impressive size. This isn't just speculation. Scientific studies have shown direct correlations between lower temperatures and increased maximum body size in various marine species, lending strong support to this temperature-related hypothesis. However, the exact physiological mechanisms that link slow metabolism, cold temperatures, and ultimate body size still present an open scientific mystery, a biological debate that continues to unfold in laboratories and on research vessels. So you've got food scarcity and cold temperatures slowing things down, allowing for a longer growth period. But there's another major player in this deep-sea drama: pressure. Imagine the weight of 100 fully loaded jumbo jets pressing down on you. That's a rough idea of the pressure at the bottom of the Mariana Trench, the deepest part of the ocean. Even at shallower, deep-sea depths, the pressure is immense, thousands of times greater than at the surface. You might think such crushing forces would reduce size, squishing creatures down. But strangely, it seems to have the opposite effect, at least on some of these organisms. One theory suggests that high pressure affects cell size and metabolism in a way that favors larger cells and slower metabolic rates, which, as we just discussed, can lead to increased body size over time. It's a bit like a pressure cooker, but instead of speeding things up, it slows them down and allows for more material to accumulate. Another idea is that a larger body size offers better structural integrity in high-pressure environments. A bigger, more robust body might simply be better equipped to withstand the constant, immense squeeze without collapsing. Think of a very small, delicate object versus a large, solid one under pressure. The larger one might actually distribute the force more effectively. This is still a hotly debated topic among scientists, with different hypotheses vying for prominence. The precise mechanisms by which extreme pressure influences an organism's ultimate size are a fascinating open scientific mystery. We're still piecing together how their proteins, cell membranes, and internal structures cope and adapt to such an extraordinary force. Beyond these environmental factors, there's also the element of predation. In the vast, dark emptiness of the deep, encounters with predators might be less frequent than in the bustling, shallower waters. If you're a creature that's rarely preyed upon, there's less selective pressure to stay small and agile to avoid being eaten. Instead, the selective pressure might shift towards being larger, which can deter potential predators or make you a less appealing meal. If a smaller predator does come along, a larger body size can simply make you too big to handle, ensuring your survival. It's a bit like an arms race, where size itself becomes a formidable defense. Another less discussed but plausible theory relates to reproductive strategies. In environments where encounters are rare, such as the sparsely populated deep sea, having a larger body might increase the chances of successful reproduction. A larger organism can potentially produce more eggs or sperm, increasing the odds of finding a mate and successfully propagating its species. They might also be able to store reproductive material for longer, waiting for just the right moment or the rare encounter. This isn't just about sheer numbers. It's about the increased capacity and longevity that a larger body might afford in a challenging environment. It's a pragmatic approach to ensuring the continuation of life against incredible odds. So when you put it all together, the scarcity of food leading to efficient metabolisms, the cold temperatures allowing for longer lifespans, the immense pressure influencing cellular processes, and the reduced predation pressure, you start to see a complex web of environmental factors that converge to favor gigantism in the deep sea. It's not one single cause, but a symphony of extreme conditions that orchestrate the evolution of these magnificent, oversized creatures. It's a testament to life's incredible adaptability, a biological marvel playing out in the dark, silent depths. It's truly a strange world down there. We, with our delicate bodies and reliance on sunlight, would simply crumple under the immense weight of the water, freeze in the perpetual chill, and starve in the food deserts. Yet, these creatures thrive, not just surviving, but flourishing into sizes that defy our terrestrial expectations. They are living proof that life, when given enough time and subjected to the right evolutionary pressures, can adapt to virtually any extreme, pushing the boundaries of what we imagine possible. It makes you wonder, what are the secrets the still largely unexplored deep ocean holds? What other giants are lurking, waiting to be discovered, patiently growing larger and larger in the eternal night? The more we learn, the more we realize how little we actually know about the vast majority of our own planet. Now that we've explored the why behind deep-sea gigantism, let's meet some of these truly enormous insects. And when I say insects, remember we're talking about arthropods, the larger phylum that includes insects, spiders, and crustaceans. Our first giant is one you might recognize in a much smaller form from your garden or under a damp log, the isopod. But these aren't your typical roly-polies or woodlice. We're talking about the giant isopod, specifically species like Bathynomus giganteus. Imagine a woodlouse, but instead of fitting in the palm of your hand, it's the size of a football, or even larger, up to 76 centimeters, 30 inches, long, and weighing over a kilogram, 2.5 pounds. You might chuckle at the thought, but picture encountering one of these armored behemoths scuttling across the abyssal plain, its many legs moving deliberately. They look like something straight out of a low-budget sci-fi movie, a prehistoric relic brought to life. Their bodies are segmented and hard, almost like a knight's armor, providing excellent protection in an environment where even a small collision could be catastrophic. They have large, complex eyes that are surprisingly well developed for a creature living in perpetual darkness, suggesting they can detect bioluminescent flashes or subtle light cues from distant food sources. The giant isopod is a benthic scavenger, meaning it lives on the seafloor and feeds on whatever edible material drifts down from above. This includes dead whales, fish, and even decaying wood. Their scavenging lifestyle is a perfect adaptation to the food-scarce deep sea. When a large foodfall occurs, like a whale carcass, these isopods converge on it in incredible numbers, gorging themselves. They are known to be able to go for extremely long periods without food. We're talking years. One famous example involved an isopod in an aquarium that survived for over 5 years without eating a single bite. This incredible endurance is a direct consequence of their extremely slow metabolism, a hallmark of deep sea life we discussed earlier. It allows them to patiently wait for the rare, unpredictable feast. This capacity for prolonged fasting is a mainstream scientific fact, consistently observed in both captive and wild specimens, showcasing their incredible resilience. Despite their formidable appearance, giant isopods are generally not considered active predators. They are the cleanup crew of the deep, essential for recycling nutrients back into the ecosystem. Without them and other scavengers, the vast amounts of organic material that sink to the bottom would simply accumulate, locking away vital nutrients. They play a crucial role in the deep-sea food web, transforming decaying matter into their own biomass, which can then be consumed by other, larger predators. Although exactly what preys on adult giant isopods is another open scientific mystery. Their tough exoskeletons probably deter most attackers, but it's believed that deep-sea sharks or some of the larger octopuses might occasionally snack on them. This lack of clear predators further reinforces the idea that reduced predation pressure contributes to their ability to grow so large. So while they might resemble oversized versions of something you'd squash with your shoe, the giant isopods are magnificent examples of how life adapts to the most extreme conditions on Earth. They are slow, patient, and armored, perfectly suited to their role as the deep sea's ultimate recyclers. Their very existence reminds us that size is relative, and what might be considered a small creature on land can become a colossal titan in the alien world of the abyss. They truly embody the phrase, live slow, grow big, a testament to evolution's ingenuity in the face of immense pressure and eternal darkness. From the armored tanks of the deep, we move to creatures that, despite their often minuscule size in shallow waters, also exhibit impressive gigantism in the abyss, the amphipods. When you hear amphipod, you might think of tiny shrimp-like crustaceans that scuttle along beaches or live in tide pools, barely an inch long. But in the deep sea, particularly in the extreme pressures of ocean trenches, some amphipods grow to truly surprising dimensions, becoming what scientists sometimes call supergiants. Take, for example, Alicella gigantea, found in the Kermadec Trench in the Pacific. This amphipod can reach lengths of up to 34 centimeters, 13 inches. Imagine a shrimp longer than your forearm. Another notable giant is Hirundellea gigas, which has been found in incredible numbers in the deepest parts of the Mariana Trench. While not as long as Alicella, it's still significantly larger than its shallow water relatives, thriving in conditions that would instantly crush most other forms of life. These aren't just isolated incidents. The phenomenon of gigantism among amphipods seems to be particularly pronounced in the Hadal zone, the deepest parts of the ocean trenches below 6,000 meters. So why do these seemingly delicate creatures become so large in the most extreme environments on Earth? The same principles of abyssal gigantism we discussed earlier apply here, but perhaps with an added emphasis on the unique conditions of the trenches. The immense pressure in these hadal zones is thought to play a significant role. It's speculated that very high pressure can alter the fundamental biochemistry of cells, potentially slowing metabolic rates even further and allowing for more extended growth periods. There's also the idea that in such an incredibly desolate environment, where food is even scarcer than in the abyssal plains, a larger body size might be crucial for efficient food acquisition and storage. You have to make the most of every meal, and a bigger gut helps with that. Amphipods are typically scavengers, much like the giant isopods. They possess powerful mandibles, adapted for tearing apart decaying organic matter, whether it's marine snow or the remains of larger animals that fall into the trenches. Some species are also thought to be detritivores, feeding on general organic debris. Their sheer numbers in certain trench environments suggest that they are highly successful at exploiting these limited food resources. Imagine dropping a small piece of bait into a deep trench. Within minutes, it can be swarmed by hundreds, if not thousands, of these deep-sea amphipods, a truly remarkable sight that highlights their efficiency as cleanup crews. One fascinating aspect of giant amphipods, and an open scientific mystery, is their mobility and distribution. How do these relatively slow-moving creatures manage to find rare food falls across vast, dark trench systems? Do they have an exceptionally developed sense of smell or chemical detection? Are there currents that help distribute them, or do they simply rely on sheer numbers and chance encounters? The exact mechanisms of their dispersal and foraging strategies in such an enormous, uniform environment are still being actively researched. Understanding how they navigate and find sustenance in such a challenging landscape is crucial to fully grasping their ecological role. The existence of these supergiant amphipods challenges our preconceptions about life at the extremes. They prove that even tiny, common creatures can evolve into formidable giants when faced with the relentless pressures and unique opportunities of the deep-sea trenches. They are a testament to life's ability to not just survive, but to thrive and grow to incredible proportions, even in the most inhospitable corners of our planet. From the armored scavenging isopods and the supergiant amphipods of the trenches, let's turn our attention to another group of deep-sea arthropods that might send a shiver down your spine if you're not a fan of terrestrial arachnids. The pycnogonids, commonly known as sea spiders. Now, these aren't true spiders in the way you think of them, spinning webs in your attic. They belong to their own distinct class of marine arthropods, but their appearance, long, spindly legs radiating from a tiny body, earns them their common name. And in the deep sea, some of these sea spiders are truly enormous. While most shallow water sea spiders are small, often just a few millimeters to a couple of centimeters across, their deep sea cousins can be giants. Some species have a leg span of up to 70 centimeters, 28 inches, or more. Imagine a creature with legs so long and thin that it looks like a living underwater tumbleweed, slowly ambling across the seafloor. Their bodies, by contrast, remain remarkably small, often no bigger than a thumbnail, making their extreme leg length even more striking. This disproportionate size gives them an almost alien appearance, as if they were designed by an artist with a penchant for the bizarre. The reason for this extreme leg length, particularly in the deep, is another fascinating aspect of abyssal gigantism. One prevailing theory is that these long legs help them move across soft, silty seafloors without sinking, acting like natural snowshoes. In an environment where food is sparse, being able to cover a larger area efficiently to find scattered prey or detritus is a significant advantage. It's like having a built-in search party for your next meal. Another hypothesis suggests that the long legs increase their sensory reach, allowing them to detect chemical cues or subtle movements in the water over a wider area, effectively tasting or feeling their way through the dark. This is a mainstream scientific idea, supported by observations of their slow, deliberate movements. What do these leggy giants eat? Unlike terrestrial spiders, sea spiders are not web spinners. Many deep-sea pycnogonids are thought to be predators or scavengers, using their proboscis, a long straw-like mouthpart, to suck up fluids from soft-bodied invertebrates like sea anemones, sponges, or even detritus. Some are also known to prey on hydroids. Their long legs might also help them gently maneuver over their prey without disturbing it, allowing them to precisely deploy their proboscis. The sheer abundance of sponges and anemones in some deep-sea environments might explain how these giants can sustain themselves despite their slow metabolism. One intriguing open scientific mystery regarding deep-sea pycnogonids is their respiration. Unlike many marine animals, they lack a dedicated respiratory system like gills. Instead, they are thought to absorb oxygen directly through their thin body surface and their extremely long, thin legs. This unusual method of gas exchange might be more efficient in the cold, oxygen-rich waters of the deep sea, where oxygen solubility is higher. However, exactly how sufficient oxygen is circulated to their entire, sprawling body, especially to the tips of those incredibly long legs, remains a subject of debate. Are their legs simply so thin that diffusion is enough? Or are there subtle circulatory mechanisms we don't yet fully understand? This unique physiological adaptation is a puzzle that continues to intrigue marine physiologists. So while they might conjure images of creepy crawlies, the deep-sea pycnogonids are extraordinary examples of life's boundless creativity. They represent a unique evolutionary path where extreme leg length, rather than body mass, is the defining characteristic of their gigantism, perfectly tailored for life in the vast, silent, and immensely pressured world of the abyss. They are truly one of the more peculiar residents of Earth's hidden depths. Now, let's talk about the titans that truly capture the human imagination, the stuff of legend and nightmare, the giant squid. These aren't insects, or even arthropods, of course, but cephalopods, highly intelligent mollusks related to octopuses and cuttlefish. However, their sheer awe-inspiring size and their elusive nature make them the undisputed monarchs of deep-sea gigantism. And frankly, you can't discuss deep-sea giants without them. For centuries, the giant squid, Architeuthis dux, was a creature of myth, known only through anecdotal accounts, pieces of carcasses found in whale stomachs, and the occasional washed-up specimen. Imagine the sheer terror and wonder of early sailors, encountering an eye the size of a dinner plate, or a tentacle thicker than a human leg. The giant squid is truly colossal. While historical accounts often exaggerated their size, scientifically confirmed specimens indicate they can reach lengths of up to 13 meters, 43 feet, for females, including their two long feeding tentacles and around 10 meters, 33 feet, for males. Their eyes are among the largest in the animal kingdom, roughly the size of a human head, or even larger, enabling them to gather as much faint light as possible in the perpetual darkness of their habitat. These incredible eyes are a mainstream scientific fact, a testament to their adaptation to the deep, too. For a long time, the giant squid remained one of the most mysterious large animals on Earth. It wasn't until 2004 that scientists captured the first ever clear images of a live giant squid in its natural habitat, off the coast of Japan. Before that, every piece of knowledge was gleaned from dead specimens or indirect evidence. This extreme elusiveness is part of its mystique. It lives in the mesopelagic and bathypelagic zones, generally at depths of 300 to 1,000 meters, 1,000 to 3,300 feet, which are incredibly difficult environments for humans to explore. This deep habitat is one of the primary reasons they remained hidden for so long. Their diet primarily consists of deep-sea fish and other squid, which they ambush using their two incredibly long feeding tentacles, armed with suckers and sharp hooks, to snatch prey from the water. Once captured, the prey is pulled towards their powerful beak, located at the center of their arms, which is capable of tearing flesh. Sperm whales are known to be their primary predators, bearing the telltale sucker marks on their bodies from epic battles in the abyss. These titanic struggles are a true testament to the power of both creatures. One of the biggest open scientific mysteries surrounding the giant squid is its behavior and social structure. Do they live solitary lives, or do they interact with others of their kind? How do they find mates in such a vast, dark, and sparsely populated environment? Are there specific mating rituals? Our direct observations are so limited that we know almost nothing about their day-to-day lives, their hunting strategies, or their reproductive cycles. Every sighting, every piece of footage offers only the briefest of glimpses into a truly alien existence. The vastness of their habitat makes sustained observation incredibly challenging, leaving us with more questions than answers about these legendary cephalopods. The giant squid stands as a powerful symbol of the ocean's enduring mysteries. It reminds us that even in our technologically advanced age, there are still vast, unexplored realms on our own planet, teeming with life we barely understand. The elusive, enormous form of Architeuthis ducks continues to fuel our imagination, inspiring awe and wonder at the sheer scale of life in the deep. If the giant squid sparks wonder, then its even larger cousin, the colossal squid, ignites a sense of profound awe and perhaps a touch of terror. You might think, how could anything be bigger than the giant squid? Well, Mesonicoteuthis hamiltoni is here to answer that question with a resounding yes. Discovered only relatively recently through fragmented remains and specimens found in the stomachs of sperm whales and Patagonian toothfish, the colossal squid is believed to be the largest invertebrate on Earth by mass, potentially weighing over 500 kilograms, 100 pounds, and reaching lengths of 12 to 14 meters, 39 to 46 feet, though precise measurements are difficult due to the limited number of intact specimens. What sets the colossal squid apart, besides its immense bulk, are its truly monstrous eyes. These are the largest known eyes in the entire animal kingdom, possibly up to 30 to 40 centimeters, 12 to 16 inches, in diameter, the size of a soccer ball or even a car tire. Imagine looking into an unblinking orb, that large, perfectly adapted, to peer into the inky blackness. These enormous eyes are a mainstream scientific fact, offering unparalleled light-gathering ability, crucial for detecting faint bioluminescent flashes from prey or predators in the perpetual twilight and darkness of the Southern Ocean's depths. Unlike the giant squid, which has suckers on its tentacles and arms, the colossal squid is armed with something far more formidable: swiveling hooks. Its arms and tentacles are lined with sharp, rotating hooks, some with multiple points, designed for grasping and tearing prey. This is a crucial distinction and offers a chilling glimpse into its predatory prowess. These hooks leave telltale, deep, crescent-shaped scars on the bodies of sperm whales, indicating truly brutal battles in the deep. It's a bit like imagining a boxing match, where one contender has actual blades strapped to their gloves. The colossal squid primarily inhabits the frigid deep waters of the Southern Ocean, surrounding Antarctica. It lives at depths of 300 to 2,500 meters, 1,000 to 8,200 feet, even deeper than the giant squid. Its diet is thought to consist mainly of deep-sea fish, like Patagonian toothfish, which we call Chilean sea bass on our dinner plates, and perhaps other squid. It's an ambush predator, using its massive eyes to spot prey and its formidable hooks to secure it. Its primary predator, like the giant squid, is the sperm whale, a titanic struggle playing out in the dark, icy depths. One of the most significant open scientific mysteries surrounding the colossal squid is its reproductive cycle and lifespan. We have even less information about Mesonychoteuthis than Architeuthis. How long do they live? When and how do they reproduce in such a cold, dark, and vast environment? Do they have a single, massive reproductive event like some other cephalopods? Or do they reproduce multiple times? The limited number of specimens, often immature or damaged, makes it incredibly challenging to piece together their full life history. Unraveling these details would provide crucial insights into the ecology of the Southern Ocean's deep-sea ecosystem. The colossal squid, with its truly unparalleled size and fearsome armaments, remains a creature of profound mystery, a living testament to the extremes of evolution in Earth's most challenging environments. It reminds us that there are still truly unknown, gigantic creatures lurking in the vast, unexplored depths of our planet, waiting to be fully revealed. From the formidable, hook-armed squid giants, we now descend further into the realm of the soft-bodied, intelligent, and often bizarre deep-sea octopuses. When you think of an octopus, you might imagine a clever, camouflaged creature darting among coral reefs. But in the crushing darkness of the deep, octopuses have evolved in ways that seem to defy imagination, growing to impressive sizes and adopting truly unique forms. While not quite as massive as the colossal squid, some deep-sea octopuses exhibit a form of gigantism that is distinct and equally captivating. Consider the giant Pacific octopus, Enteroctopus duflini, which, while not exclusively deep-sea, certainly inhabits deeper, colder waters and holds the record as the largest known octopus species by mass and arm span. Individuals have been recorded with arm spans exceeding 9 meters, 30 feet, and weighing over 270 kilograms, 600 pounds. Imagine encountering an 8-armed creature that could wrap its tentacles around a small car. Even though they're not strictly abyssal giants, their size is a powerful example of how cold water can foster incredible growth in cephalopods. This species showcases the potential for gigantism in the octopus lineage, even if it often ventures into shallower, albeit still deep, environments. Then there are the truly deep-sea specialists, like the Dumbo octopus, Grimpoteuthis species. While not giants in the same sense as the giant Pacific octopus, some species can still be quite large for an octopus living in the extreme depths, reaching up to 1.8 meters, 6 feet in length. Their charming common name comes from the prominent ear-like fins that protrude from the top of their bell-shaped bodies, which they flap to propel themselves through the water, much like the famous Disney elephant. These fins are a mainstream scientific fact, a unique adaptation for locomotion in their deep, pressure-filled world, where jet propulsion, common in other octopuses, might be less energy efficient. Deep-sea octopuses have developed a suite of incredible adaptations for life in the dark. Many species have greatly reduced ink sacs, as ink would be useless in a lightless environment for escaping predators. Their skin is often translucent or a deep red, perfectly camouflaged against the darkness or the filtered blue light that penetrates the mesopelagic zone. Some species are gelatinous, allowing them to withstand pressure changes and conserve energy. Their arms are often equipped with fewer but larger suckers or even sensory filaments, reflecting a reliance on touch and chemoreception, rather than sight for hunting and navigating. Their feeding strategies vary. Many are thought to be sit-and-wait predators, patiently ambushing small fish, crustaceans, and worms that happen to drift by. Others might slowly move along the seafloor, using their arms to explore and capture prey hidden in the sediment. Their extremely slow metabolic rates, a common theme among deep-sea giants, allow them to go for long periods between meals, making the most of every feeding opportunity. One major open scientific mystery concerning deep-sea octopuses is their reproductive behavior and parental care. We know that many shallow water octopuses exhibit remarkable maternal care, guarding their eggs for months or even years without feeding. Given the extreme cold and slow metabolism of the deep sea, it's hypothesized that deep-sea octopuses might have even longer brooding periods, potentially stretching for several years. Imagine guarding eggs for half a decade or more. The exact duration and intensity of parental care and how they manage to survive without sustenance during such prolonged periods remains largely unknown due to the immense difficulty of observing them in their natural habitat. This extended brooding period would contribute to their overall longevity, allowing them to reach impressive sizes. These deep-sea octopuses, from the truly massive to the bizarrely beautiful Dumbo, are a testament to the versatility of cephalopod evolution. They showcase how a lineage known for its intelligence and adaptability can transform itself to thrive in the most challenging and alien environments on our own planet, continuing to surprise and intrigue us with every rare glimpse. Having explored the intelligent and often enigmatic deep-sea octopuses, let's now drift into the realm of the truly ethereal, the gigantic jellyfish. When you imagine a jellyfish, you probably picture a translucent, bell-shaped creature gently pulsating in coastal waters. But in the deep sea, some jellyfish evolve into forms so immense and ghostly, they seem more like pulsating phantom blooms than living creatures. These aren't just larger versions. Their scale can be truly astonishing, transforming them into some of the most spectacular, if rarely seen, giants of the abyss. The most famous example is the lion's mane jellyfish, Cyanea capillata. While not exclusively a deep-sea resident, it can be found in colder surface waters. Its tentacles can reach truly mind-boggling lengths, making it a fitting member of our giant club. One specimen found washed ashore in Massachusetts in 1865 reportedly had a bell diameter of 2.3 meters, 5 feet, and tentacles stretching an astonishing 37 meters, 120 feet. That's longer than a blue whale, the largest animal on Earth. Imagine a living, stinging net trailing for over 100 feet through the water. While such extreme lengths are rare, the potential for incredible tentacle extension is a mainstream scientific fact for this species, a testament to its unique feeding strategy. However, truly deep-sea jellyfish often take on even more alien forms. Consider the big red jellyfish Tiburonia grandrojo. First described in 2003, this magnificent creature has a bell that can reach over a meter, 3 feet, in diameter, and is a striking deep red color. A common camouflage in the deep, where red light is quickly absorbed, making red objects appear black. Unlike many jellyfish with long trailing tentacles, Tiburonia has thick, fleshy oral arms that are thought to be used for capturing prey, or perhaps even for propulsion. It's a truly robust and substantial jellyfish, living at depths between 600 and 1,500 meters, 2,000 to 5,000 feet. Another fascinating deep-sea giant is the Periphylla periphylla, often called the crown jellyfish. While its bell doesn't reach the immense sizes of the lion's mane, it's one of the most common and widely distributed deep-sea jellyfish, and its robust, often purplish-red bell can still be quite large, up to 30 centimeters, 12 inches, in diameter. It's a stunning sight, constantly pulsating with bioluminescent flashes as it drifts through the darkness. The gigantism in these deep-sea jellyfish can be attributed to the familiar factors: cold temperatures, which slow metabolism and extend lifespans, allowing for more growth, and food scarcity, which favors large, efficient feeders that can go for long periods between meals. Many deep-sea jellyfish are passive ambush predators, simply drifting and letting prey collide with their expansive tentacles or oral arms. A larger surface area, provided by immense bells or extremely long tentacles, increases their chances of encountering scarce food items. It's a massive, living trap, drifting through the abyss. One significant open scientific mystery surrounding gigantic deep-sea jellyfish is their ecology and life cycles. Unlike many shallow water jellyfish with complex life stages involving polyps attached to the seafloor, many deep-sea species appear to be holoplanktonic, meaning their entire life cycle occurs in the water column. How do these vast, often solitary creatures find mates in the immense dark ocean? Do they rely on chemical cues or bioluminescent signals? How do their larvae develop and disperse? The deep-sea environment makes observing these crucial life history stages incredibly difficult, leaving many fundamental questions unanswered about their reproduction and population dynamics. Every time we encounter one of these majestic pulsating giants, it feels like a rare privilege, a glimpse into a world of profound mystery. From the ethereal, pulsating forms of giant jellyfish, let's burrow a little deeper, both literally and metaphorically, into the often overlooked world of deep-sea worms. When you hear worm, You might think of a small, squiggly creature, perhaps digging in your garden. But in the deep ocean, worms come in an astonishing array of forms and can reach truly incredible sizes, defying our terrestrial notions of what a worm can be. These aren't just longer, they're often robust, highly specialized, and crucial components of deep-sea ecosystems. Perhaps the most famous examples of deep-sea gigantism among worms are the giant tube worms, Riftia pachyptila. These are not true insects, but annelids, segmented worms. While they don't move around, they are astonishingly large, growing up to 2.4 meters, 8 feet, in length, with a diameter of up to 4 centimeters, 1.6 inches. Imagine a cluster of living, white tubes tipped with bright red plumes, swaying gently in the superheated, chemical-rich waters around hydrothermal vents. Their discovery in the late 1970s revolutionized our understanding of life on Earth, proving that complex ecosystems could thrive without sunlight, fueled instead by chemosynthesis. This is a mainstream scientific fact, a cornerstone of deep-sea biology. These giant tube worms are unique because they lack a mouth, gut, and anus. Instead, they host billions of symbiotic bacteria within a specialized organ called a trophosome. These bacteria perform chemosynthesis, converting hydrogen sulfide and other chemicals from the hydrothermal vents into organic compounds, which the worm then absorbs for nutrition. The vibrant red plume you see is filled with hemoglobin, much like our blood, which binds and transports sulfide and oxygen to the bacteria. It's an incredibly efficient, mutually beneficial relationship that allows them to tap into a unique energy source. Beyond the iconic tube worms, there are other remarkable examples of deep-sea gigantism in the worm world. Consider the giant marine bristleworm, Unis aphroditoa, a fearsome polychaete worm that can grow over 3 meters, 10 feet long. These predatory worms burrow into the seafloor, with only their sensory appendages exposed, waiting to ambush unsuspecting fish or other invertebrates. Their powerful jaws and numerous bristles give them a truly intimidating appearance, a far cry from the docile earthworms you might be used to. Another fascinating group are the Nemertea, or ribbon worms. While not all species are gigantic, some deep-sea ribbon worms can reach truly astonishing lengths when fully extended. Reports exist of specimens stretching over 30 meters, 100 feet or more, making them potentially the longest animals on Earth. Though these measurements are often difficult to confirm in their natural contracted state. They are typically slow-moving predators or scavengers, using a proboscis to capture prey. The reasons for gigantism in deep-sea worms align with the general principles we've discussed. Cold temperatures leading to slow metabolism and extended growth, and perhaps the lack of strong currents in some areas, allowing for delicate, elongated forms to thrive without being torn apart. For filter feeders or chemosynthetic organisms, a larger body surface or volume can maximize contact with scarce food particles or essential chemicals. One intriguing open scientific mystery regarding these giant deep-sea worms, especially the chemosynthetic tube worms, is their dispersal mechanisms. Given their reliance on specific ephemeral hydrothermal vent fields, which are like isolated oases on the vast seafloor, how do their larvae manage to find new, active vents when the old ones die out? It's like finding a needle in a haystack, but the haystack is the entire deep ocean. Do they have incredibly long-lived larvae? Or do they somehow detect chemical plumes from distant vents. Understanding how these sessile giants colonize new habitats is crucial for comprehending the resilience and connectivity of deep-sea chemosynthetic ecosystems. It's a biological puzzle of epic proportions. We've explored some of the most impressive giants of the deep, from armored isopods to colossal squid and massive tube worms. Now, let's illuminate another pervasive and utterly magical aspect of their world: bioluminescence. Imagine a world where the only light comes from the living creatures themselves, where every flash, glow, and sparkle is a message, a warning, or an invitation. That's the reality for most of the deep ocean. Bioluminescence, the production of light by living organisms, is not just a strange phenomenon. It's a fundamental part of deep-sea survival and communication, a widespread scientific fact that turns the abyss into a living light show. Almost 90% of deep-sea organisms are estimated to be bioluminescent. Think about that for a moment. The vast majority of life in the largest habitat on Earth generates its own light. This isn't just for aesthetics. Every flicker and glow serves a crucial purpose. From the twinkling lights on the belly of a cookie-cutter shark to the mesmerizing, intricate patterns on some deep-sea jellyfish, bioluminescence is the language of the dark. One of the primary uses of bioluminescence is for predation. Many deep-sea fish, like the famous anglerfish, use a bioluminescent lure to attract unsuspecting prey. Imagine a small glowing fishing rod dangling in the pitch black, drawing curious fish close enough to be devoured by the anglerfish's massive toothy maw. Other predators use flashes of light to disorient or startle prey, making them easier to catch. Some squid and fish even release a cloud of glowing fluid, similar to ink, to create a smoke screen that distracts a predator while they make their escape. It's a clever trick, like throwing glitter in a dark room and vanishing. Bioluminescence is also vital for defense. Some organisms use bright flashes to startle or temporarily blind predators, giving them a precious few seconds to flee. Others employ what's called burglar alarm bioluminescence. When attacked by a predator, they emit light to attract an even larger predator to the scene, essentially calling for help or creating a diversion. Imagine a small shrimp flashing wildly, drawing a bigger fish that then goes after its original attacker. It's a risky but often effective strategy. Still others use counter-illumination, where they produce light on their undersides to match the faint sunlight filtering down from above, effectively camouflaging themselves from predators looking up from below. This makes their silhouette disappear against the faint background light. And then there's communication and mating. In a world without light, visual signals are produced by the organisms themselves. Many species use specific patterns or frequencies of light to attract mates, like fireflies in the night, but underwater. Different species have unique light codes to ensure they attract the right partner, a vital adaptation for reproduction in a sparsely populated environment. Some scientists even speculate about complex light-based social interactions, though much of this remains in the realm of open scientific mystery. The precise language of these light signals, how they are generated with such specificity, and the full extent of their communicative roles are still largely unknown. We can see the lights, but we don't yet understand the full conversation. The chemicals involved in bioluminescence are often highly specialized, typically involving a molecule called luciferin and an enzyme called luciferase. When these react, they produce light with very little heat, making it an incredibly efficient process. Cold light for a cold world. The ability of these deep-sea creatures to harness chemical reactions to create their own illumination is a truly awe-inspiring aspect of their biology, turning the vast darkness into a dynamic, living spectacle. As we continue our journey through the deep, illuminated by the ghostly glows of bioluminescence, let's confront one of the most immediate and profound challenges of this environment: pressure adaptations. You're sitting comfortably, likely with only the weight of the air above you. Now imagine descending into the ocean. For every 10 meters, 33 feet, you go down, the pressure increases by 1 atmosphere, or about 14.7 pounds per square inch. At the average depth of the ocean, around 3,800 meters, 12,500 feet, the pressure is over 380 atmospheres, which translates to thousands of pounds per square inch. This is enough to crush a human, collapse a submarine not designed for it, and flatten most terrestrial life forms instantly. So, how do these deep-sea giants, including our insects and other colossal creatures, not only survive but thrive under such immense, crushing forces? The answer lies in a remarkable suite of biological and physiological adaptations, a mainstream scientific fact that continues to amaze researchers. Firstly, deep-sea organisms generally lack the air-filled spaces that collapse under pressure in land animals. No lungs, no gas bladders, or greatly reduced specialized ones. They are mostly composed of water, which is largely incompressible. Think of a bag of water. You can squeeze it as hard as you like, but it won't reduce significantly in volume. Their bodies are essentially pressure equalized with their surroundings, meaning the internal pressure is equal to the external pressure, so there's no crushing differential. However, it's not just about being squishy. The immense pressure affects the very biochemistry of life. Proteins, for instance, can lose their shape and function under high pressure, a process called denaturation. To counteract this, deep-sea creatures have evolved unique proteins that are more rigid and stable under pressure. They also produce special organic molecules called piezolites, from piezo, meaning pressure, and light, meaning soluble substance. One of the most common piezolites is trimethylamine N oxide, or TMADO. This molecule helps stabilize proteins and enzymes, preventing them from denaturing under extreme pressure. It's like a molecular bodyguard for their essential biological machinery. The more pressure a creature lives under, generally, the more TMAO it has in its cells. This is a remarkable adaptation that allows their fundamental life processes to continue functioning. Furthermore, their cell membranes, which are crucial for regulating what goes in and out of cells, are also adapted. In shallow water organisms, cell membranes can become too rigid under pressure, hindering vital cellular processes. Deep-sea organisms often have more unsaturated fatty acids in their cell membranes, which keeps them more fluid and functional even under extreme pressure. It's like having a flexible protective barrier that doesn't crack or stiffen under stress. Despite these incredible adaptations, the very forces that allow them to survive also play a role in their gigantism. As we touched on earlier, some theories suggest that high pressure itself can lead to slower metabolic rates and longer lifespans, contributing to their larger size over extended growth periods. The sheer energetic cost of maintaining cellular integrity under such conditions might also favor larger, more efficient bodies. However, there's still an open scientific mystery regarding the upper pressure limits of complex life. We know that life can thrive in the deepest trenches, down to nearly 11,000 meters. But beyond that, it seems to peter out. Is there a fundamental biological limit to how much pressure proteins and cellular structures can withstand, even with piezoites and specialized membranes? Or are there simply no more energy sources or other resources to sustain life beyond those depths? The precise mechanisms that define the absolute physiological boundaries of life under ultra-high pressure remain an active area of research, pushing the frontiers of astrobiology and our understanding of habitability. It makes you wonder if pressure, in its own way, is the ultimate barrier. As we consider the immense pressure faced by deep-sea inhabitants, let's now shift our focus to an equally defining challenge of the abyss: food scarcity. Imagine living in a world where edible sustenance is as rare and unpredictable as a shooting star. That's the daily reality for the creatures of the deep ocean, where photosynthesis, the basis of most life on Earth, cannot occur due to the absence of sunlight. This extreme lack of consistent food has driven the evolution of some truly remarkable strategies, contributing significantly to the phenomenon of gigantism. In the vast majority of the deep sea, far from hydrothermal vents, the primary source of food is marine snow. This is a continuous, slow drizzle of organic debris drifting down from the productive surface waters. Dead plankton, fecal pellets, discarded larval shells, and other detritus. It's like a perpetually falling, incredibly sparse, nutrient-poor snowstorm. While constant, it's rarely enough to sustain a large active organism with a high metabolism. For larger deep-sea creatures, relying solely on marine snow would be akin to trying to survive on a handful of crumbs a day. This leads to the crucial strategy of feast and famine. Instead of constant small meals, deep-sea giants often rely on infrequent, massive food falls. The ultimate examples of these are whale falls, where the carcass of a large whale sinks to the seafloor, providing an enormous, localized buffet that can sustain entire communities for years or even decades. Other large falls can include dead fish, sharks, or even large masses of kelp that detach from coastal areas and drift into the abyss. When such a bonanza occurs, scavengers like the giant isopods and amphipods we discussed earlier converge in staggering numbers, gorging themselves. Their adaptation to this feast or famine existence includes several key features that contribute to their large size. Firstly, slow metabolism is paramount. By operating at an incredibly low energy burn rate, they can conserve energy and survive for extended periods, sometimes years, without food. This allows them to wait patiently for the next, unpredictable meal. Think of them as ultra-efficient biological engines, sipping fuel rather than guzzling it. This is a mainstream scientific fact, widely observed across various deep-sea phyla. Secondly, many deep-sea giants have developed large, expandable stomachs or guts. This allows them to consume enormous quantities of food when it becomes available, storing the energy reserves, often as lipids or fats, to tide them over during the long periods of starvation. Imagine being able to eat a month's worth of food in one sitting and process it slowly over time. This capacity is a direct physical manifestation of their adaptation to an irregular food supply. Some organisms, like certain deep-sea fish, can swallow prey larger than themselves, expanding their jaws and stomachs to accommodate. Thirdly, many deep-sea giants are generalist scavengers or opportunistic predators. They aren't picky eaters. If it's organic and edible, they'll likely consume it. This broad diet increases their chances of finding sustenance in a resource-limited environment. An open scientific mystery concerning food scarcity and gigantism is the interplay between infrequent, large food falls and the background marine snow. How do these two food sources differentially impact the growth rates and ultimate maximum sizes of deep-sea giants? While we know large food falls are critical, does the constant trickle of marine snow provide enough baseline energy to simply sustain life, allowing the massive growth spurts to occur only during large feasts? Or do certain species rely more heavily on one over the other for their growth trajectory? The precise metabolic accounting of how these different energy inputs translate into the astonishing sizes we observe is still being fully elucidated. A complex balance sheet that evolution has perfected, building on the challenges of immense pressure and profound food scarcity. Let's now delve into another critical environmental factor that profoundly shapes deep-sea life: cold temperatures. Imagine a perpetual winter, but without the snow and ice on the surface, just a consistent, bone-chilling cold that permeates everything. Below about 1,000 meters, 3,300 feet, the vast majority of the ocean remains incredibly cold, typically hovering between 2 to 4 degrees Celsius, 35 to 39 degrees Fahrenheit, and often even colder, near freezing point in polar deep waters. This frigid environment is not just uncomfortable. It's a powerful sculptor of life and a key contributor to the gigantism we observe. The most direct impact of these icy temperatures is on metabolism. For cold-blooded, ectothermic creatures, which make up the vast majority of deep-sea life, lower temperatures mean slower metabolic rates. This is a fundamental principle of biology, a mainstream scientific fact. Chemical reactions, including those vital for life, simply proceed at a much slower pace when it's cold. Think of food stored in a refrigerator. It spoils much more slowly than on a countertop. Similarly, a creature's internal processes slow down, burning energy at a significantly reduced rate. This slow metabolism directly contributes to gigantism in a few crucial ways. Firstly, it allows these organisms to live longer. If your life processes are running in slow motion, your lifespan is effectively extended. Instead of maturing and reproducing quickly, deep-sea creatures can take decades or even centuries to reach maturity. And with a longer lifespan comes more time for growth. Even if the rate of growth is incredibly slow, a prolonged existence allows for the accumulation of more biomass, leading to larger overall body sizes. It's the tortoise and the hare principle applied to evolution. Slow and steady wins the race to giant proportions. Secondly, the slow metabolism directly ties into the food scarcity issue we just discussed. If you're burning energy at an incredibly low rate, you don't need to eat as frequently. This means you can survive for much longer periods between those rare, large food falls or on the meager trickle of marine snow. Your energy reserves stretch further, allowing you to endure the prolonged famine periods common in the abyss. It's an energy-saving masterclass. Beyond metabolism, cold temperatures also influence the physical properties of the water itself. cold water is denser and holds more dissolved oxygen than warmer water. This higher oxygen content might be beneficial for large organisms, as they can extract more oxygen from each gulp of water, even with a slower respiratory rate. However, the viscosity of cold water is also higher, making movement more energetically costly. This might explain why many deep-sea giants are slow-moving or rely on passive feeding strategies rather than active pursuit predation. An open scientific mystery related to cold temperatures and gigantism is the precise physiological mechanisms that allow some deep-sea species to actively grow in such frigid conditions rather than just stagnate. While we understand the general principle of slow metabolism leading to longer life and thus more growth time, the molecular adaptations that facilitate continuous, albeit slow, protein synthesis and cell division at near freezing temperatures are still being fully elucidated. Are there specific enzymes that function optimally in the cold, or unique chaperone proteins that ensure proper folding? And how does this interplay with the pressure adaptations we discussed earlier? The exact biological blueprint for constructing and maintaining a massive body in perpetual cold remains a complex and fascinating area of research, continually pushing the boundaries of our biochemical understanding. Having navigated the chilling embrace of the deep's cold temperatures, let's turn our attention to one of life's most fundamental processes, made uniquely challenging in the abyss: reproduction. In a world defined by vast emptiness, crushing pressure, and perpetual darkness, finding a mate, successfully reproducing, and ensuring the survival of offspring presents an extraordinary set of hurdles. Yet life persists, and these deep-sea giants have evolved fascinating, albeit often mysterious, strategies for deep-sea love and the continuation of their species. One of the biggest challenges for reproduction in the deep sea is simply finding a mate. Imagine searching for a single individual in a volume of water larger than all the continents combined, with no light to guide you. This extreme sparsity often leads to specialized adaptations. Many deep-sea organisms, as we've discussed, use bioluminescence for this very purpose. Specific flashing patterns or steady glows can serve as recognition signals, attracting potential partners from afar, like a Morse code message exchanged across the vast darkness. This is a mainstream scientific fact, widely observed in various deep-sea fish, crustaceans, and cephalopods. Each species often has its own unique light display, preventing accidental interspecies encounters. Another strategy to overcome mate scarcity is hermaphroditism, where an individual possesses both male and female reproductive organs. This doubles the chance of a successful encounter, as any two individuals that meet can potentially reproduce. This is common in some deep-sea invertebrates. For other species, like certain anglerfish, the male is a tiny parasitic creature that permanently fuses with the much larger female, effectively becoming a living sperm dispenser. This ensures that once a male finds a female, he never lets go, guaranteeing reproductive success. It's a rather dramatic form of commitment, wouldn't you say? The deep sea's cold temperatures and slow metabolism also mean that reproductive cycles are often incredibly slow and prolonged. Deep-sea animals often take many years, even decades, to reach sexual maturity. Once they do, gestation periods or egg brooding times can also be significantly extended. For instance, some deep-sea octopuses are believed to brood their eggs for years, meticulously guarding them without feeding. This slow pace of life means fewer reproductive events over an extremely long lifespan, but each event has a higher chance of success due to the extended care. This contributes to their gigantism, as a longer pre-reproductive period allows for more growth. The energy investment in reproduction is also immense. Producing large, yolk-rich eggs or live young that are well developed and capable of surviving the harsh environment is a common strategy. Instead of releasing millions of tiny, vulnerable larvae, some deep-sea giants produce fewer, larger offspring with better chances of survival. This ensures that the limited energy available is concentrated into quality rather than quantity. One of the most intriguing open scientific mysteries concerning deep-sea reproduction is the social structures and communication cues during mating in species that don't visibly bioluminesce or are not parasitic. How do giant isopods, for instance, find each other across vast abyssal plains? Do they release chemical pheromones that drift for miles through the cold currents, silently calling to potential mates? The detection and interpretation of such chemical signals in a three-dimensional, dark, and often turbulent environment present a significant scientific challenge. Understanding these unseen forms of deep-sea dating would unlock crucial insights into the population dynamics and evolutionary success of these hidden giants. It truly shows that love, or at least the drive to reproduce, finds a way even in the most challenging environments. As we consider the extraordinary challenges of deep-sea life, from immense pressure to perpetual cold and scarce food, we now arrive at an exception to many of these rules, a vibrant oasis of life fueled by a truly alien energy source: chemoautotrophy. Most life on Earth, including everything we've discussed so far, ultimately relies on the sun's energy, either directly through photosynthesis or indirectly by consuming organisms that do. But around hydrothermal vents and cold seeps, entire ecosystems flourish without a single ray of sunlight, driven by chemical energy. This revolutionary discovery, a mainstream scientific fact, forever changed our understanding of where and how life can thrive. Imagine towering chimneys on the seafloor, spewing superheated water, rich in dissolved minerals and chemicals like hydrogen sulfide, methane, and various metals, into the frigid abyss. These are hydrothermal vents, often found along mid-ocean ridges where tectonic plates pull apart. The water emerging from these vents can be as hot as 400 degrees Celsius, 750 degrees Fahrenheit, but it doesn't boil due to the immense pressure. Around these vents, life explodes into existence, supporting unique communities of organisms, including some of our giant insects and other colossal invertebrates. The foundation of these ecosystems isn't photosynthesis, but chemosynthesis. Instead of using sunlight, specialized microorganisms, bacteria and archaea, use the chemical energy from the vent fluids to produce organic matter. They convert inorganic compounds, particularly hydrogen sulfide, into sugars and other nutrients. Much like plants convert sunlight into sugars, these chemosynthetic microbes form the base of the food web, supporting a diverse array of life, including the iconic giant tube worms we mentioned earlier. Giant tube worms, Riftia pachyptila, are perhaps the most striking examples of gigantism fueled by chemosynthesis. As we discussed, they lack a mouth and gut, relying entirely on symbiotic bacteria living within their bodies. These bacteria perform the chemosynthesis, providing the worm with all its nutritional needs. The worm's bright red plume absorbs sulfide and oxygen from the vent fluid, delivering it to the bacteria. This allows the worms to grow incredibly rapidly compared to other deep-sea creatures, sometimes reaching lengths of over 2 meters in just a few years. Their gigantism here is a direct result of an abundant and localized energy source, rather than a slow accumulation over a long lifespan in food-scarce environments. Other deep-sea giants found in vent and seep environments include large mussels, clams, and even crabs, all thriving by either directly consuming chemosynthetic bacteria or forming symbiotic relationships with them. For example, some giant mussels house chemosynthetic bacteria in their gills, creating a highly efficient food factory within their own bodies. The deep-sea yeti crab, Kiwa hirsuta, with its hairy claws, is thought to farm chemosynthetic bacteria on its bristles, which it then scrapes off and eats. It's like having a built-in pantry, an intriguing open scientific mystery related to chemosynthetic ecosystems and their giants is the connectivity and genetic flow between isolated vent fields. Hydrothermal vents are scattered like tiny hot islands across the vast cold seafloor, often thousands of kilometers apart. When one vent field becomes inactive, how do the larvae of these highly specialized, giant organisms manage to find and colonize new active vent sites? Is it sheer luck carried by currents, or do they possess sophisticated sensory abilities to detect distant chemical plumes? The genetic evidence suggests some level of connectivity, but the exact mechanisms of dispersal over such immense distances remain largely unknown. A truly epic journey for microscopic larvae. It's a biological puzzle that highlights the incredible resilience and interconnectedness of life in the deep. From the vibrant, chemically fueled oases of hydrothermal vents, let's now consider another remarkable, albeit transient, source of localized abundance in the food-scarce deep: whale falls. Imagine the largest animal on Earth, a majestic whale, reaching the end of its life journey and slowly, silently, sinking through thousands of meters of water to the abyssal plain. What might seem like a tragic end for one creature is, in fact, the beginning of a spectacular, long-lasting feast for a diverse community of deep-sea organisms, including many of our giants. A whale fall is a mainstream scientific fact, a natural phenomenon that creates a unique temporary ecosystem, a true oasis in the deep-sea desert. When a whale carcass settles on the seafloor, it provides an enormous bounty of organic matter, blubber, muscle, and bones that can sustain life for decades, even centuries. This single event can significantly impact the surrounding deep-sea community, drawing in organisms from vast distances. It's like finding a fully stocked supermarket dropped in the middle of a barren plain. The decomposition of a whale fall typically occurs in several distinct stages, each attracting different sets of organisms. The first stage is the mobile scavenger stage. Within hours or days of the whale hitting the bottom, highly mobile scavengers, like the giant isopods and amphipods we discussed, along with deep-sea sharks and hagfish, arrive in droves. They quickly consume the soft tissues, stripping the carcass down to the bone in a matter of months or a year. These are the feast periods we talked about, where creatures gorge themselves, storing energy for future lean times. Next comes the enrichment opportunist stage. Once the initial frenzy of scavenging subsides, a more diverse community of worms and crustaceans colonizes the sediments enriched by the decomposing organic matter. These creatures feed on the remnants of flesh and the bacteria that thrive on it. But the most fascinating stage, and where the longevity of the whale fall truly shines, is the sulfophilic stage. As the whale's bones begin to decay under anaerobic, oxygen-free conditions, they release lipids and other organic compounds. Specialized bacteria then break down these compounds, producing hydrogen sulfide, much like the chemicals found at hydrothermal vents. This sulfide, in turn, fuels a chemosynthetic community, similar to those at vents, but on a smaller, more localized scale. These are often giant, specialized organisms. For example, unique species of bone-eating worms, Osidax species, often called zombie worms, colonize the bones, using root-like structures to absorb nutrients. These worms, while not massive themselves, represent an incredible adaptation to this specific, long-term food source. The contribution of whale falls to deep-sea gigantism is indirect but significant. They provide rare, massive energy infusions that allow scavengers to grow large and accumulate reserves. For the specialized organisms of the sulfophilic stage, they offer stable, long-term energy sources, allowing for sustained growth within that specific niche. Whale falls essentially act as stepping stones, connecting distant chemosynthetic communities and providing vital ecological corridors. An intriguing open scientific mystery surrounding whale falls is their role as evolutionary stepping stones for chemosynthetic life. Scientists debate whether whale falls, being more common and widespread than hydrothermal vents, might have acted as training grounds or dispersal points for chemosynthetic species, allowing them to evolve and then colonize the more permanent but widely separated vent systems. Do the unique fauna of whale falls represent a distinct evolutionary lineage, or are they closely related to vent species, utilizing these temporary food sources to bridge vast distances? Understanding this evolutionary connection would provide crucial insights into the origins and distribution of chemosynthetic life across the entire deep ocean, revealing how these isolated oases came to be populated by their unique, often gigantic, inhabitants. We've explored the extraordinary food sources and physical conditions that shape deep-sea life. Now, let's consider another fundamental aspect of survival in the abyss: sensory adaptations. Imagine living in a world of perpetual night, where the concept of sunlight is utterly foreign. How do you find food, avoid predators, and locate mates when your primary sense, vision, is seemingly useless? The answer is that deep-sea creatures have evolved a breathtaking array of specialized senses, often radically different from those of their shallow water cousins, that allow them to see and interact with their world in truly alien ways. Vision in the deep sea is predictably highly specialized. While the very deepest parts are entirely devoid of sunlight, the upper deep sea zones, the mesopelagic, still receive faint, filtered blue light. Here, many deep-sea fish and cephalopods have evolved enormous eyes that are exceptionally sensitive to this specific wavelength of light. The colossal squid, as we discussed, has the largest eyes in the animal kingdom, designed to capture every photon of light available, whether it's the last vestiges of sunlight or the flashes of bioluminescence. Their eyes often contain a high concentration of rhodopsin, a light-sensitive pigment, and lack color vision, as differentiating colors would be pointless in a monochromatic world. This extreme ocular adaptation is a mainstream scientific fact, evident in countless deep-sea species. However, below the mesopelagic, where sunlight never penetrates, vision becomes less about external light and more about detecting bioluminescence. Many organisms have highly sensitive eyes tuned to the specific wavelengths of light produced by other deep-sea creatures. Some even have tubular eyes that point upwards, likely to spot silhouettes of prey or predators against the faint light from above, or to detect the distant flickers of bioluminescence. For creatures living in the absolute crushing darkness, their eyes are essentially sophisticated bioluminescence detectors. But in areas of complete darkness, or for creatures that don't rely on visual cues, other senses become paramount. Chemoreception, or the sense of smell and taste, is incredibly important. Many deep-sea scavengers, like our giant isopods and amphipods, have highly developed antennae and chemosensory organs that can detect minute traces of chemicals, such as those released by a decaying whale carcass, from miles away, guiding them to their next meal. Imagine being able to smell a meal dropping thousands of feet above you and slowly sinking down. Mechanoreception, the sense of touch and vibration, is also crucial. The lateral line system in deep-sea fish, for example, is often highly developed, allowing them to detect subtle water movements caused by approaching prey or predators. Many invertebrates have delicate sensory hairs or filaments that can feel the slightest currents or disturbances. The long legs of deep-sea pycnogonids, for instance, are thought to be packed with sensors, allowing them to explore their environment and find food. An open scientific mystery revolves around the integration and processing of these diverse sensory inputs in the deep-sea brain. How do these creatures combine information from ultra-sensitive eyes, sophisticated chemical detectors, and highly tuned mechanoreceptors to build a coherent picture of their world? Is there a hierarchy of senses, or are they equally weighted? Understanding the neural architecture and cognitive processes of deep-sea organisms, particularly those that exhibit gigantism and potentially complex behaviors, is incredibly challenging given our inability to study them directly. It truly makes you ponder the incredible and often alien ways that different life forms perceive their reality. As we contemplate the incredible sensory adaptations of deep-sea life, let's delve into another remarkable characteristic that often goes hand in hand with gigantism in the abyss: lifespan. Imagine living for centuries, growing slowly and deliberately, experiencing the passing of human generations, while you simply continue to exist in the cold, dark depths. Many deep-sea giants exhibit extraordinary longevity, far exceeding their shallow water counterparts. This extended lifespan is not merely a curious fact. It's a fundamental consequence of their environment and a key enabler of their enormous size. The primary driver behind this remarkable longevity is, as we've discussed, the cold temperatures of the deep sea, combined with the extreme food scarcity. When metabolism slows down due to frigid conditions, all life processes, growth, development, aging, and even reproduction, also slow considerably. It's like life itself is playing out in slow motion. This means that a creature that might live for a few years in warmer, shallower waters could live for decades or even centuries in the deep. This extended lifespan provides ample time for continuous, albeit very slow growth, allowing these organisms to reach colossal sizes. This live slow, die old strategy is a mainstream scientific fact, consistently observed across various deep sea taxa. Consider some of the stunning examples. Greenland sharks, Somniosus microcephalus, which inhabit cold deep waters in the North Atlantic and Arctic, are now known to be the longest living vertebrates on Earth. Studies estimate their maximum lifespan to be at least 272 years, and possibly up to 500 years. Imagine a shark that was alive when the American Revolution happened, still swimming in the deep today. While not an insect, it powerfully illustrates the longevity conferred by cold, deep environments. The giant Antarctic isopod, while not quite as long-lived as the Greenland shark, can live for many decades, far exceeding the lifespan of its shallow water relatives. Its famed ability to survive for years without food is directly tied to its ultra-slow metabolic rate. Deep-sea corals, such as Gersemia antarctica, can live for thousands of years, building vast, ancient structures in the abyss. While sessile, their longevity is another testament to the extreme slowing of life processes. This longevity isn't just about surviving, it's about enabling growth to epic proportions. If you have 100 or 200 years to grow, even a fraction of an inch per year can add up to impressive dimensions. It's a fundamental trade-off. In exchange for a slow, arduous existence, they are granted incredible durability and the time required to become giants. However, this extended lifespan also presents unique challenges, particularly for reproduction. If individuals take many decades to reach sexual maturity and live for centuries, the time between generations becomes incredibly long. This can make adaptation to rapid environmental changes very difficult, as natural selection acts over much longer timescales. An open scientific mystery revolves around the cellular and molecular mechanisms of aging and repair in these exceptionally long-lived deep-sea giants. How do their cells maintain integrity and function for so long without accumulating debilitating damage? Are there unique DNA repair mechanisms, antioxidant defenses, or protein maintenance systems that allow them to defy senescence for centuries? Understanding the anti-aging secrets of these deep-sea centenarians could have profound implications for human longevity research. The deep ocean, in its cold, dark embrace, seems to hold the key to an extended existence, a biological fountain of youth, if you will, but one that comes with the price of a perpetually slow and challenging life. Having marveled at the astounding longevity of deep-sea giants, let's now address the immense practical challenge of even knowing they exist. Discovery challenges. Imagine trying to study creatures in a habitat that is not only vast and dark, but also incredibly remote, crushing, and frigid. It's like trying to explore another planet without ever leaving Earth's atmosphere. The deep sea, despite being our planet's largest habitat, remains largely unexplored, making the discovery and study of its colossal inhabitants a monumental task. This profound difficulty is a mainstream scientific fact, driving continuous innovation in marine technology. The primary obstacle is, of course, the extreme environment itself. Standard diving equipment is useless below a few hundred meters. To reach the depths where these giants reside, scientists require highly specialized and incredibly expensive submersibles, or remotely operated vehicles, ROVs, capable of withstanding pressures thousands of times greater than at the surface. These vehicles are complex marvels of engineering, designed with reinforced hulls, powerful lights to pierce the gloom, and sophisticated manipulators to collect samples. Deploying and operating them requires extensive logistical planning, highly trained crews, and often takes weeks or months for a single expedition. Secondly, the vastness and uniformity of the deep sea make finding specific organisms incredibly difficult. It's an enormous volume of water, and many of these giants are sparsely distributed. Imagine trying to find a particular type of large animal in an area the size of an entire continent, but in 3 dimensions, and with no light. This is why many discoveries happen serendipitously, through trawling nets or by chance encounters with ROVs. The very elusiveness that contributes to their mystique also makes them incredibly hard to study directly. Thirdly, the behavior of deep-sea creatures often compounds the discovery challenge. Many are slow-moving, ambush predators, or scavengers that conserve energy, meaning they don't move around much to increase their chances of being seen. Others might be highly sensitive to light or disturbances, retreating from the bright lights and noise of submersibles. Even when a specimen is captured, bringing it to the surface alive is often impossible due to the drastic pressure and temperature changes, meaning most studies are conducted on dead or preserved specimens. This makes understanding their natural behavior incredibly difficult. Consider the giant squid, which remained largely a creature of myth until the 21st century. Despite centuries of whaling and fishing, direct observations in its habitat were virtually non-existent. It took decades of persistent effort, technological advancements, and a stroke of luck to capture the first images of a live Architeuthis ducks. The colossal squid remains even more elusive, known primarily from specimens hauled up in fishing nets or found in whale stomachs. An open scientific mystery stemming from these discovery challenges is the true diversity and maximum size of deep-sea life. Given that such a small fraction of the deep sea has been explored, some estimates say less than 5% has been visually observed, what other colossal creatures are still out there, completely unknown to science? Are there even larger species of giant isopods, undiscovered species of colossal squid, or entirely new forms of life waiting to be revealed? Our current understanding of abyssal biodiversity and maximum size is undoubtedly incomplete, limited by our technological capabilities and the sheer scale of the environment. Every new expedition into the deep has the potential to rewrite our textbooks, revealing yet another hidden giant. Given the formidable discovery challenges we just discussed, it's clear that unlocking the secrets of deep-sea giants fundamentally relies on continuous advancements in technological advancements. You see, without the right tools, the deep ocean remains an impenetrable fortress. Over the past few decades, incredible strides in marine engineering and robotics have gradually pulled back the curtain on this hidden world, allowing us to observe, sample, and understand its colossal inhabitants in unprecedented ways. These technological leaps are a mainstream scientific fact, constantly pushing the boundaries of deep-sea exploration. One of the most critical developments has been the creation of increasingly sophisticated submersibles, both crewed and uncrewed. Early submersibles, like the Bathyscaphe Trieste, made groundbreaking descents, but were limited in maneuverability and observation capabilities. Modern human-occupied vehicles, HOVs, such as the Alvin or the Shinkai 6500, allow scientists to descend into the deep, directly observing and interacting with the environment. Imagine sitting in a tiny sphere, looking out a thick viewport as a giant isopod scuttles by, or a Dumbo octopus flaps its way through the darkness. The personal experience these vehicles offer is invaluable, providing context and intuition that remote systems can't fully replicate. However, the real revolution has come with remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs. ROVs are uncrewed robots tethered to a surface ship, controlled by operators who see through their cameras and manipulate their arms. They can stay underwater for much longer periods than HOVs, operate in more hazardous conditions, and dive deeper. ROVs like Hercules, Jason, and the Nereus, though Nereus was a hybrid ROV or UV that was sadly lost, have provided us with the vast majority of our stunning deep-sea footage and crucial scientific samples, including the first direct observations of the giant squid. They are equipped with high-definition cameras, powerful lights, sonar, and highly precise manipulators. AUVs, on the other hand, are untethered, pre-programmed robots that can cover vast areas of the seafloor independently, mapping, collecting data, and even taking samples. They are like silent, tireless explorers, charting the unknown. The combination of these technologies allows for a multi-pronged approach to exploration. AUVs for broad surveys, ROVs for detailed close-ups and sampling, and HOVs for human-led reconnaissance and scientific intuition. Beyond the vehicles themselves, advancements in camera technology have been pivotal. Low-light cameras, high-definition video, and specialized lighting techniques have transformed murky, dark images into clear, vibrant footage, revealing the true colors and behaviors of deep-sea creatures. Acoustic imaging, using sound waves, allows us to see through sediment and water, detecting large objects like whale falls, or even mapping the seafloor with incredible precision. Even sophisticated molecular techniques play a role. Environmental DNA, eDNA analysis, for example, allows scientists to detect the presence of specific species, including potentially unknown giants, from tiny traces of DNA shed into the water, without ever having to see or capture the organism itself. This non-invasive method is an exciting frontier in deep-sea discovery. An intriguing open scientific mystery arising from these technological advancements is how the presence and activities of these exploration vehicles affect the natural behavior of deep-sea giants. Do the bright lights disorient them? Does the noise scare them away, or perhaps even attract them? While we strive for minimal impact, the act of observation itself can alter the observed. Scientists continually debate how to deploy technologies in a way that provides the most accurate and undisturbed insights into the true lives of these elusive creatures, ensuring our discoveries are genuinely reflective of their undisturbed existence in the vast, silent abyss. While technological advancements are rapidly expanding our understanding of deep-sea giants, they also, paradoxically, bring into sharper focus a sobering reality: conservation concerns. You might think that creatures living thousands of meters down, in a seemingly untouched world, would be safe from human impact. Unfortunately, this is increasingly not the case. The very technologies that allow us to explore the deep also enable us to exploit its resources, leading to growing threats to these ancient and often slow-growing ecosystems. The vulnerability of the deep sea to human activity is a pressing mainstream scientific fact. One of the most significant threats comes from deep-sea fishing. As shallow water fish stocks become depleted, fishing fleets are venturing into deeper waters, targeting species like Patagonian toothfish, which, as you remember, are prey for colossal squid or deep-sea sharks. Trawling, particularly bottom trawling, is incredibly destructive. Massive weighted nets are dragged across the seafloor, indiscriminately scooping up everything in their path, including fragile deep-sea corals, sponges, and countless other invertebrates. This practice devastates delicate habitats that have taken centuries or millennia to form, destroying the homes and food sources of many deep-sea giants and their associated communities. Imagine a bulldozer scraping across a pristine ancient forest. That's the impact of bottom trawling on the seafloor. Another growing concern is deep-sea mining. As terrestrial mineral resources become scarcer, there's increasing interest in exploiting mineral deposits found on the seafloor, such as polymetallic nodules, cobalt-rich crusts, and massive sulfide deposits around hydrothermal vents. While the technology for widespread deep-sea mining is still developing, the potential for environmental devastation is enormous. Mining operations would disrupt vast areas of the seafloor, creating plumes of sediment that could smother filter feeders, release toxic chemicals, and destroy the unique, often chemosynthetic, ecosystems that support giant tube worms and other specialized life forms. Given the extremely slow growth rates and long lifespans of many deep-sea species, any damage would take an unimaginably long time to recover, if at all. Plastic pollution also reaches the deepest parts of the ocean. Microplastics have been found in the guts of deep-sea organisms, including amphipods from the Mariana Trench. Larger plastic debris, like bags and bottles, litters the seafloor, entangling animals and introducing harmful chemicals. It's a stark reminder that even the most remote corners of our planet are not immune to our waste. Furthermore, noise pollution from shipping, seismic surveys for oil and gas, and deep-sea mining exploration can disrupt the delicate sensory worlds of deep-sea creatures, interfering with their ability to navigate, communicate, and find food. For animals that rely on subtle vibrations or sound cues, this constant cacophony can be profoundly disorienting, an open scientific mystery, and a significant challenge in deep-sea conservation is the lack of baseline data and comprehensive ecological understanding. Because so little of the deep sea has been explored, scientists often don't know what a healthy deep-sea ecosystem looks like, or the full extent of its biodiversity. This makes it incredibly difficult to assess the true impact of human activities, or to set effective conservation targets. How do you protect something when you don't even know what you're protecting, or how it functions? It's a race against time to understand these ecosystems before they are irreversibly altered by human hands, highlighting the urgent need for continued research and precautionary principles in managing the deep ocean. Beyond the immediate threats of fishing and mining, a pervasive, insidious danger looms over the deep sea and its magnificent giants: climate change's deep impact. You might assume that the vast, cold, and stable abyss would be insulated from the warming temperatures and other disruptions occurring at the surface. However, the deep ocean is far from immune. It's intricately connected to surface processes, and the changes we are causing globally are slowly but inexorably permeating even the most remote depths. This profound connection and the potential for deep-sea impact are a growing mainstream scientific concern. One of the most direct impacts is ocean warming. While the deep ocean warms much more slowly than the surface, it is warming. Even a slight increase in temperature in the abyss can have significant consequences for creatures adapted to consistently cold conditions. Remember how crucial cold temperatures are for their slow metabolism, extended lifespans, and ultimately, their gigantism? A rise in temperature could disrupt these fundamental biological processes, potentially altering growth rates, reproductive cycles, and metabolic efficiency. For species that have evolved over millennia to function optimally at near freezing temperatures, even a few degrees of warming could be catastrophic, pushing them beyond their physiological limits. Another major concern is ocean deoxygenation. As ocean waters warm, their capacity to hold dissolved oxygen decreases. Additionally, changes in ocean circulation patterns, driven by warming, can reduce the amount of oxygen-rich water flowing into the deep. This leads to the expansion of oxygen minimum zones, OMZs, areas where oxygen levels are so low that most complex life cannot survive. As OMZs expand and deepen, they effectively shrink the habitable space for deep-sea organisms, including our giants. Imagine your home slowly being filled with an invisible gas that makes it harder and harder to breathe. That's the reality for creatures caught in expanding OMZs. Ocean acidification is also a significant threat. As the ocean absorbs increasing amounts of carbon dioxide from the atmosphere, its pH decreases, making it more acidic. This acidification primarily impacts creatures that build shells or skeletons out of calcium carbonate, such as corals, clams, and some crustaceans. While some deep-sea species are more resilient, prolonged exposure to more acidic waters can make it harder for them to form and maintain their structures, weakening their defenses or hindering their growth. Even if a giant isopod's tough exoskeleton isn't directly dissolving, the health of the broader ecosystem it depends on could be compromised. Changes in food supply are another indirect but critical impact. Climate change affects surface ocean productivity through changes in temperature, currents, and nutrient availability. Any reduction in primary productivity at the surface means less marine snow raining down into the deep, exacerbating the already challenging issue of food scarcity. This could lead to reduced growth rates or even starvation for deep-sea giants, particularly those that rely on occasional large food falls. An open scientific mystery is the threshold and tipping points for deep-sea ecosystems in the face of climate change. How much warming, deoxygenation, or acidification can these ancient, slow-paced ecosystems withstand before irreversible changes occur? We have very limited long-term data from the deep sea, making it incredibly difficult to predict the exact cascades of impact. Will deep-sea gigantism become a relic of a past climate? Will the slow pace of deep-sea life make them inherently more vulnerable, unable to adapt quickly enough to rapid environmental shifts caused by human activity? The long-term consequences remain a profound and urgent unknown. a silent environmental drama unfolding beneath billions of tons of water. Having acknowledged the profound creeping impacts of climate change on the deep, let's step back and consider the deeper implications of these discoveries. The world of deep-sea giants isn't just a collection of bizarre creatures. It's a living, breathing testament to the utterly alien nature of our own planet. It is, in essence, Earth's final frontier. When you explore the deep sea, you are not merely observing different animals. You are witnessing ecosystems and forms of life that operate on principles so distinct from our surface world that they feel like they belong on another celestial body. Think about it. A realm without sunlight, where life is fueled by chemicals from Earth's core, or sustained by food that literally rains down from above, where pressure can crush steel and temperatures hover near freezing, yet creatures grow to colossal sizes and live for centuries. This isn't just an extreme environment, it's a parallel biosphere, a vibrant reminder that life can find a way no matter how harsh the conditions. The deep sea challenges our anthropocentric views of what life needs to survive and thrive. This concept of the deep sea as an alien world on Earth is a mainstream scientific idea, frequently discussed in astrobiology circles. The exploration of the deep sea offers invaluable insights for the search for extraterrestrial life. If life can exist and even flourish in such extreme conditions on Earth, in total darkness, under immense pressure, drawing energy from chemical reactions, then the possibilities for life on other planets or moons in our solar system become far more plausible. Imagine the subsurface oceans of Europa, Jupiter's moon, or Enceladus, Saturn's moon. These icy worlds are believed to harbor vast liquid water oceans warmed by geological activity, potentially containing hydrothermal vents. The discoveries in Earth's deep sea provide a blueprint for what life might look like and how it might sustain itself in such extraterrestrial environments. They tell us that life doesn't always need a warm, sunny surface to flourish. The sheer diversity and novelty of deep sea life also constantly challenge our understanding of evolution. Every new discovery, whether it's a giant unclassified worm or a previously unknown chemosynthetic community, expands the tree of life and reveals unexpected evolutionary pathways. It shows us that nature's imagination is far grander than our own, perpetually pushing the boundaries of biological form and function. The very existence of abyssal gigantism itself is an evolutionary puzzle that continues to yield insights into fundamental biological processes. Furthermore, the deep sea is a vast, largely untouched repository of biodiversity and genetic resources. Many deep-sea organisms produce unique enzymes or biochemical compounds that allow them to function under extreme conditions. These extremolites hold immense potential for biotechnology, offering new medicines, industrial processes, or insights into resilient materials. It's a vast biological library, and we've only just begun to read the first few pages. However, the alienness also highlights our profound responsibility. Because it's so different and so difficult to access, it's also incredibly vulnerable. The delicate balance of these ancient ecosystems, built over millennia, can be easily disrupted by human activity. The slow pace of life means that recovery from disturbance is almost impossibly long. This fragile grandeur underscores the importance of protecting this final frontier before we understand its full value. The deep sea isn't just some dark, empty void. It's a vibrant, bizarre, and crucially important part of our living planet, a constant source of wonder and a reminder of the extraordinary ingenuity of life. And so we arrive at future exploration. Mysteries still await. You might think that with all our advanced technology and the incredible discoveries we've discussed, we must be close to fully understanding the deep sea. The truth, however, is far more humbling. Despite our breakthroughs, the vast majority of the deep ocean, especially its very deepest parts, remains completely unexplored. It is arguably the least understood major habitat on Earth, a boundless realm teeming with unseen wonders and unanswered questions. This ongoing state of profound mystery is a mainstream scientific reality that continues to drive scientific endeavor. Consider the sheer scale. Over 60% of Earth's surface is covered by ocean depths greater than 1,000 meters. The average depth is nearly 4 kilometers, and the deepest trenches plunge to almost 11 kilometers. We have better maps of the surface of Mars than we do of our own seafloor. Only a tiny fraction of the deep sea floor has been visually observed or sampled. This means that for every giant isopod, colossal squid, or bizarre Dumbo octopus we've discovered, there are likely countless others, perhaps even more enormous or more alien, still completely unknown to science. The future of deep-sea exploration promises to reveal even more about abyssal gigantism. Scientists are developing new generations of submersibles and ROVers capable of diving to the very deepest parts of the Hadal Zone with greater agility and endurance. These new tools are equipped with even more sensitive sensors, advanced cameras, and sophisticated sampling equipment, allowing us to probe the most extreme environments with unprecedented detail. Imagine tiny, autonomous robots swarming a whale fall, collecting data for weeks, or super strong materials, allowing us to build even more robust observatories on the seafloor. One major area of future exploration involves the continued search for new hydrothermal vent and cold seep communities. We've only found a fraction of these chemically driven oases. Each new discovery has the potential to reveal entirely new species, including giant worms or clams adapted to unique chemical signatures, further expanding our understanding of chemosynthetic life and its limits. The mapping of the global ocean floor, still largely incomplete, will undoubtedly lead to the discovery of many more of these life-supporting hotspots. Another frontier is the exploration of the subsea floor biosphere. We now know that life exists deep within the sediments and even the rocky crust beneath the ocean floor. While not home to giants in the traditional sense, understanding these deep biosphere ecosystems and their interactions with the water column could shed light on the ultimate limits of life and the cycling of critical elements, potentially even influencing the food web that supports larger deep-sea creatures. Perhaps the most exciting aspect of future exploration is the potential for truly unexpected discoveries. The history of deep-sea science is replete with instances where new technologies have revealed forms of life that defy all previous biological understanding. Will we find an even larger, more elusive cephalopod? Will there be creatures that use entirely new forms of energy or communication? The open scientific mystery is not just what we will find, but how these unknown giants and ecosystems operate, and what fundamental laws of biology they might challenge or confirm. The deep ocean is still Earth's greatest natural laboratory, holding secrets that could revolutionize our understanding of life itself. Every expedition, every new descent is a step further into a world that continues to surprise, inspire, and humble us, reminding us that the greatest adventures often lie hidden closest to home, beneath the waves. And now, as the gentle currents of our imagination carry us away from the inky depths and their colossal inhabitants, feel the silent vastness of the ocean begin to recede. The colossal eyes, the sprawling tentacles, the slow, deliberate movements of giants in the eternal dark. They fade into the quiet murmur of your own thoughts. The deep sea is a place of ancient calm, where time stretches out in a way we can barely comprehend. The pressures that shape these creatures, the cold that cradles their long lives, the scarcity that demands such incredible resilience. These forces are still at play, silently crafting new wonders beneath unimaginable weights of water. They are the patient custodians of Earth's oldest secrets, living testaments to life's boundless ingenuity. Let your mind drift softly now, like marine snow falling through endless blue. Imagine the gentle pulse of a Dumbo octopus, the slow crawl of a giant isopod across unseen plains. These giants are out there, living their long, quiet lives, a universe away from our bustling surface world, yet intricately connected to the planet we share. There's a profound peace in that thought, a sense of wonder at the vastness of existence, both seen and unseen. As the last echoes of their immense silent world whisper away, feel yourself settling, becoming lighter, warmer. The journey is over for now, but the mystery, the wonder, the quiet awe of what lies beneath will always remain. Close your eyes now and let the gentle currents of sleep carry you away into dreams as vast and as deep as the ocean itself.